step to you with a corny line, asking for your name, saying what's your sign. You turn around like, boy, quit talking to me.
This is about improper integrals. So, what is an improper integral? So this term, improper. So I suppose you could say that so far what we've been doing are proper integrals in the sense that we've had a bounded region, like from an a to a b. However, improper implies that you're integrating over an unbounded region. Okay, so this is unbounded region. Okay, so this basically means that one of two things. So the first case is when you're integrating from an a, so the variable stands for an actual number, so like let's say a is 2 or whatever, so some number to infinity, or it could be flipped around when you're integrating from negative infinity to a number, or even the third case could be from negative infinity all the way up to positive infinity. So these are unbounded, obviously, because the first one is unbounded on the right, second one is unbounded kind of on the left, and then the third one is just, it has no bounds at all whatsoever. Okay, so this is the first case when your interval is one or both of them are some kind of infinity, or we could have where the whole integral, so no matter what your interval, when you're integrating a function, if that comes out to be plus or minus infinity, that is also unbounded. Okay? So, common sense, you would think that an unbounded region would have like an infinite area, right? Because like if you keep going, let's say you have an unbounded region, right? And then let's say this is your A, and you want to evaluate from A all the way up to infinity, keep going, you'd think that the area underneath the curve just keeps adding and adding and adding and going up and up and up. However, this isn't necessarily true. And in the next example, I'll show you why. Okay, so let's say this is just a general case. We're integrating from 0 to r. So in this case, r is a number, all right? And let's say we have e to the negative x dx. Okay, so this is our function that we're integrating. So let's just integrate mathematically. So we have an e to the negative x, and we need a negative sign in front. And then we have evaluated from 0 to r. Right, so then let's plug this in. So then we get negative e to the negative r minus a negative e to the negative 0. So this is going to turn out to be, well, these two negatives are going to turn into positives, and this is a 1. So this is actually 1 minus e to the negative r, which is 1 over e to the positive r. Okay? So just keep this in mind. And now let's say, okay, so this was what we just did, basically. So e to the negative x, if I graph that, that's going to be, it's going to cross the y-axis. So here's our y and here's our x. It's going to cross the y-axis at 1, right? So this is 1. And then we have, it basically just comes down like this. It's the flip of e to the x. Okay? Hey, that was actually pretty good. I got kind of close. Okay, so this is what our graph looks like, e to the negative x. And then let's say, oh, we were doing it from 0, so here's 0. So we're starting here. This is our left endpoint. And we're integrating, let's say r is here, okay? Just some random number. Okay. And then, so this is what we just calculated. Area underneath the curve all the way to r. Okay, this is our 1 minus 1 over e to the r. And then, now, let's say that r, this r here, we're going to move it all the way so it goes to positive infinity. So it's just going to keep going on and on and on. All right? So now, we're going to take the limit, because, the limit as r approaches infinity. So it's going to, that was a weird arrow, hold on. Okay, so r approaches infinity. And then we're going to do this integral, because we want to know what the area is as this r is going to infinity. So then we have r 0 to r, and then e to the negative x dx. Okay, so this is what we're interested in now. And as you can see, this part, the integral, we already calculated that, right? So we could just plug that in for the integral spot. So this limit is going to be still limit as r goes to infinity, and then we're going to plug this in. 1 minus 1 over e to the r. Okay? And now from here we can just plug in our r to evaluate the limit. So then we get 1 minus 1 over e to the infinity. And as we know, e to the infinity is just going to be an infinity on the bottom, right? That's just a really huge number that we can't even calculate. And then 1, this whole thing, this fraction, 1 over infinity, turns into, it's going to tend to 0, right? Just this part. The 1 still stays in front over here. So then we have a 1 minus 0, and our limit is 1. So basically what this 1 is saying is that there is a finite area, or a set area, that the area under this curve approaches as this r, whatever number that is, goes to infinity. So even though this graph continues on and on and on, it's just going to be like the area that it keeps adding for every x, it's just going to be like infinitesimally small or something. So anyways, so this is how an unbounded region can have a finite area. Okay, so now I'm going to give you a couple of definitions. Alright, so definitions, and these are in your book. I just want to kind of highlight them so you're exposed to them and are more familiar with it. So our first one is from a to infinity. So like in the previous example, my a was 0, or this could be whatever number, some fixed number. And then we're integrating f of x dx equals, and then I'm just going to write kind of what we just did. So our r goes to infinity, and then we had a still down here, and r is our top limit, and then f x dx. Okay, so that's just the first definition. And then on the other hand, we could also have, like let's say we're coming from the left, so then we could have our negative infinity from the left, and then we go up to a certain point. So then our a is at the top. Okay, so f of x dx equals, and this is just the opposite way now. So r goes to negative infinity, and that spot is on the bottom, right? So r is on the bottom, a is on the top. Okay, so then along with these, we have to decide, let's see, if we try to evaluate, well, okay, so these are two separate cases. That's just, yeah, so one's going to infinity and the other one is coming from negative infinity. But anyways, in either of the cases, if the limit does exist, so if the limit exists, then we have that the integral, it's called converges. Okay, so that's the term that they use when you actually get a numerical answer. So the integral converges and is finite. And finite just means like a fixed number or value. Okay, whereas on the other hand, if the limit doesn't exist for some reason, so that's a no, then the integral is said to diverge. So the integral diverges, and the limit, okay, I should put limit, and limit is, well, it doesn't exist, so limit does not exist, okay? Alright, so now I'm going to go over a really important theorem that you're going to be seeing a lot. So, well, theorems, I guess. Okay, so the first one says, when you're evaluating, same thing, so a to infinity of, now we're going a little bit more specific on functions. So this is a certain category of a function called the p integral, because you have the p exponent down here. So anyways, what this is, this kind of splits up into two different pathways. So if your p is greater than 1, well, we have two different cases. When the p is greater than 1, when the power is greater than 1, and when the power is less than or equal to 1. Okay? So if p is greater than 1, then your answer for this integral is going to be a to the 1 minus p over p minus 1. Okay? And then if p is less than or equal to 1, then this integral just diverges. Okay? And then here's the second case. So then now we have from 0 to a. So see the difference here? The first one was from a certain number all the way to infinity, like the examples that we've done so far. And this one is from 0 up to a certain number. So this is actually a bounded integral. Okay? So again, we're going to have the same thing here, just the different bounds, different interval. So then we'll have 2 ways to go here. So then on this one though, the signs are the less than or greater or less than signs are flipped. So instead of p is greater than 1 on top, we're going to have less than 1. And then on the bottom we have p is greater than or equal to 1. Whoa, that was a weird one. Yeah, okay. So on the top we're going to have the same thing, a 1 minus p, and then p minus 1, and then the bottom is going to diverge. So the important thing here to notice is that the set, or I guess the p-values for case number 1 are flipped around in comparison to the second case. Okay?
No more